continuing through chapter 4. Today we're going over division. And we'll start a little bit on floating point representation. Wednesday we'll go over operations. So after Wednesday, you'll be able to finish the entirety of homework. So homework is due next Wednesday. So division, we know it's the reciprocal of multiplication. We use this less frequent usually, and it's a little harder to do in Python. So what we all remember from grade school is long division, right? So if your divisor is less than or equal to your dividend at the bit that you're at, then you put a 1 in the quotient. Like if we start at the first bit here, that's just 1. 8 is larger than 1, so we put a 0 here. And then if we add the next bit over, then 8 is still larger than 2, so we put a 0. 8 is still larger than 4, we put a 0. Now 8 is less than or equal to 9, so we put a 1. Then we subtract the 8 from the 9. We have the remainder of 1, bring the next 0 down. And 8 is bigger than 2, so we put a 0. 8 is bigger than 5, so we put a 0. And then we bring the other 0 down. And now 8 is less than 10, so we put a 1, subtract the 8 from the 10, and we get a remainder. So we do this test for every single bit, and then subtract if we can. Otherwise, we put a 0 and bring the next bit down. So this works exactly how you would do this in decimal, right? Just to define some things, the divisor is what you're dividing by. The dividend is what you're going to divide up. So the easiest way to implement this is with restoring division hardware. So with restoring division, we subtract the divisor, and then if the remainder is negative, we restore it because we did not subtract it. And then we shift the divisor to the right by 1 bit to then go to the next bit and do the same thing. Or we subtract, and if it's negative, we add the divisor back and then put a 0 in our quotient. So if it's positive, that means that we were able to subtract it. So a 1 goes in our quotient, and we do not add the divisor back. So again, this is the simple hardware version. We have our divisor. It's going to be initially in the left half over here. And then this is our quotient, where we're going to be adding all of our bits. And then our remainder is where our dividend is. So if it's all in here, we have our divisor. In the left half, we subtract, right? Then we check the remainder. Was it negative? If it was, control says add the divisor back, and then shift right. And the shift right corresponds to going to the next bit. Okay. And then if we have a negative result, we put a 0 next to it. Then we do the subtraction again, but our divisor was shifted. So now we're looking at a little bit more into the remainder. And if we have, say, a positive result in the remainder, then control will say do not add the divisor back, but add a 1 to the quotient. And then we keep doing this until we get to the end of the divisor. So we see how every iteration we're doing one of these bits. So here is, again, the flow chart. Step 1 is always subtract the divisor. Okay. If the remainder is negative, restore, and then append a 0 to quotient. If the remainder is positive, that means that you were able to subtract, so you do not restore, and quotient gets a 1. And then you always shift the divisor register to the right by 1 to go to the next bit. And then you repeat that for however many bits you have. And once you're at the end, you're done. And the remainder register has the remainder, quotient register has the quotient. So here is the simple hardware table. We have 7 divided by 2. We have, this is 7, this is 2. So the initial values, quotient is all zeros. Divisor goes into the left half of the divisor register. And remainder holds our dividend. Right? So step 1, subtract the divisor from the remainder register. This is our new value that we get. This is negative, so we add the divisor back to restore the remainder. And then we shift the divisor to the right and append a 0 to the quotient. Now that the divisor is shifted to the right, again, first thing we do is subtract. And this is, again, negative. So we restore it, quotient gets a 0, divisor gets shifted to the right. Okay. Step 3, and subtract, negative results. So quotient gets a 0, and then divisor goes to the right by 1. Iteration 4, we subtract. This time it's positive, right? The result. So that means we do not restore. We give our quotients a 1, and then we shift our divisor right. And then step 5, we again subtract, right? And we are again positive. So quotient gets 1, divisor gets shifted right by 1, and that is the end. So we have our remainder of 1, and our quotient is 3. And 7 divided by 2, 3 remainder 1, right? So this is the optimized hardware. So again, we don't want to use a 64-bit ALU if we can do it with half as much of a resource. And same thing for our divisor, it only needs to be 32 bits. And our quotient can also be stored in the remainder register, because we can store it into the. So we basically switch the order to shift the first, and then we're going to subtract, save 1 iteration. It is going to reduce the divisor and the ALU width by half. And the remainder register keeps the quotient, so there's no register for the quotient is just going to be over here. Now we're going to shift out the dividend from the remainder register because we're not using the top bits anymore as we keep going. And this, if you look at this slide and the multiplier slide, the hardware setup is the exact same. So you can use the same hardware to do division and multiplication. You just have to have the correct control signals. And we like that because we like to reuse hardware, right? So here are our steps. We shift first, and we subtract, and we do this test, right? So it's the same test, If it was positive, then your quotient gets 1 and you don't restore. If it's negative, your quotient gets 0 and you restore. And you repeat that until you're at the end. And one thing that you have to do, since we are shifting first now instead of just subtracting, we have to shift the left half of the remainder register to the right by 1 bit to do this correction and get the correct remainder. Because otherwise you have shifted it to the left 1 too many. So here is the same example. So we have our initial values, we have the divisor, and then the remainder. And now the first step is shift the remainder left by 1. Do the subtraction. So we have remainder, subtract the divisor, we get a negative result. So we restore and append the 0 as our quotient. And we also shift. Do the subtraction again between here and here. We have a negative result. So again, append to 0, shift left, and restore. Iteration 3, we're going to do our subtraction again. So we have this, and we're subtracting from this, and our result is now positive, right? So we're going to not restore, append a 1 to our quotient, and shift left. The remaining. Iteration 4. Again, we do our subtraction between here and here to get this. This is again positive. So we get a 1 and we shift left. And this was our last iteration. So we are done with the subtractions process. And our correction is to shift the left half. And it's important that you remember that it's just the left half and not the entire remainder register to the right by 1. And now you have your quotient in the right half, remainder in the left half. The quotient again is 3 and remainder is 1. And you can always double check 7 divided by 2 is 3, remainder 1, right? So your homework is to fill out these tables. So we went over the optimized and unoptimized version for multiplication and division. The homework is asking you specifically for the optimized versions of these. So look at this table and the optimized table for multiplication. Do not do this more complicated. Well, it's not more complicated. It's unoptimized. It's in a lot of ways, it's a lot easier to understand because it has more steps. But the hardware is not as optimized because it's almost twice the size. So sign division. We can again do the same thing as we did for multiplication, just add a little bit of pre-processing and add a little bit of post-processing, and you can use the same hardware to do sign division. So we're going to divide using the absolute values. And the way that we get the absolute values is just if any of our operands are negative, we convert them to positive, right? And we're going to remember the signs of our operands. And once we have the result of the remainder and the quotient, the sign of the remainder becomes the sign of the dividend. And then we're going to negate the quotient if the dividend and divisors have different signs. So we know how to put the inputs, and we can easily check that they're the same or different with XOR. And then we can flip the sign of the remainder just to match whatever the sign of the dividend was. We know how to do this in hardware? Yes. And then if we need to negate, you would negate the same way that you're negating the input if it's negative, right? Flip all the bits, add 1. So here is our example for sign. So 7 divided by 2. This is all positive, so we don't need to do any flipping. So we get that 3 and a remainder of 1. Right? And here we have -7 divided by +2. So we would flip 7 to be +7. We would get 3 with a remainder of 1. Our remainder becomes the same sign, the dividend. So we would flip it to be -1. And then our signs of the dividend and the divisor differ. So our quotient needs to be negative. We flip that too. So we get -3, remainder of negative. And you would do the same thing, or if the signs were flipped, but now your remainder is positive because your dividend is the one that's positive. Okay, so this is the end of the sign division. Before we go into MIPS, do you have any questions on this hardware? The algorithm on how to do it is just long division, right? So just like multiplication, MIPS is going to use high and low register pairs to do the 64 bits remainder register. And then if you divide by 0, it's going to do this, set the overflow flag. You need to check this with your software. So it has these 2 instructions, just like for multiply, we have divide, and then we have divide u, so div u, which is for that step. And again, here's our example. So we want to div t1 by t0, and we're going to load the lower bits into t2 and the higher bits into t3. Right. So in terms of faster division, we can't just compute all of the additions or the multiplications of the bits with the multiplier like we do for multiplication and then do a tree of adders. Because with division, we have to subtract and we don't know if we needed to restore or not. So you cannot use parallel hardware like in the multiplier because the subtraction is conditional on the sign of the remainder for each bit. So if we want to make faster divisors, the algorithms that are used are generally trying to do multiple quotient bits per iteration rather than one quotient bit per iteration. And this still requires multiple steps. Okay? So if I want to do 4-bit division, I'm doing 2 bits per step, I still take 2 steps. And then there are other schemes for division, and we're going to focus on this restoring division. If you wanted to look this up, you can. So now we'll go into floating point numbers. So floating points is used for when we need to represent numbers with fractions, but more specifically, very, very small numbers, as well as very large numbers, because we already know that we can represent numbers with fractions with fixed point representation, right? But if we have a very small number that needs to be 2 to the negative 30, then we would need a lot of bits in order to do that in fixed points. Right? We would need at least 30 bits to the right of the decimal point. So to represent these very small numbers and very large numbers, we have this floating points representation. And the reason it's called floating points is because the points can move based on the exponent base. So here's our form in decimal. So you might know this as scientific notation, right? So this is 1, 2, 3, 4 digits of significant digits. And then you have it's normalized to the power of 10. So we're going to use this same format with binary numbers. So we have this 1, and this 1 will always be implied because just like in scientific notation, you always just have one number to the left of the decimal points. We are always going to have one number to the left of the decimal points, and it's not needed if it's a 0. So it's always going to be a 1. Otherwise, it would not exist, right? Or you would just adjust your exponent. So this way we can save 1 bit. This 1 is always implied. And then we have these bits that are going to represent the fractional part, as well as we're going to use some bits to represent the exponent part. So we have 3 different fields. We have the sign bit, fraction, exponent. So the floating point standard that is used today is this IEEE standard, and it was developed in response because there was a whole lot of different diverging representations. So if we wanted to share code across different developers, if we're using 2 different representations, it makes it very difficult to share that code. You would have to convert from each representation every time that you want to use the other code. So with this standardization of floating point representation, it is now almost universally adopted. So it's very easy to now share code because we all, if you're using floating point representation, you should be using the IEEE standard representation. There are 2 different representations for IEEE floating point standards. There's single precision, which is 32 bits, and then double precision, which is 54 bits. The format is the exact same. It's the same 3 fields, sign bits, exponents, and then they call it fraction, or you'll often see it as mantissa. It's just the number of bits in the fraction or mantissa, as well as the exponent differ between the 2 representations. So this is our equation again. So we have the sign bits. If it's 1, it's negative, right? We have this implied 1, and then we're going to add the fraction to that implied 1. And then we shift it by the exponent. And there's one more thing here, because we don't want to waste space in our exponent bits, we add this bias to it, so we can get a range of positive and negative exponents without having a signed exponent bit. And this is it for our 2 representations. Sign bit is always just 1 bit. Our exponent bits for single precision is 8 bits. Double precision is 11 bits. And then our fraction bits are just the rest. So for single precision is 23 bits. Double precision is 52 bits. So if sign bit is 0, it's positive or non-negative, and then if sign bit is 1, negative. And then the fraction or mantissa is going to be the fractional part of the significand. And we, again, are always pre-appending this 1 bits. So there's no need to represent it explicitly in our representation. That's how we're saving 1 bit. And the significand is the fraction. Our exponents, we have the actual exponent is going to be like you want the number here as the whole thing. You're going to take this exponent and subtract the bias. That'll give you the real. So the bias for single precision is 127, and that's because we have 8 bits. So I can represent 256 different values with 8 bits. So if I subtract 127, about half of those values will be negative, half of them will be positive. And then for floating points, the double precision, it's 1023. And again, because we have 11 bits. So if you ever forget what the bias is, you can just look at how many bits there are. What is the closest power of 2 minus 1? That will give me half of that representation. Right, so here is our first example. We want to show the binary representation of negative 0.75 in IEEE single precision format. So what's our sign bit? 1. And what would our mantissa bits be? Which ones are our mantissa bits? No part? Yeah, just the 1. And then the rest would be all zeros, right? And then what does our exponent need to be? Yes, because we want it to be -1, but we add the bias of 127. So here is our representation. Sign bit is 1, significand. Probably one of the most common mistakes is I put that my fractional bits are 0.11, right? Because you forget that the 1 at the very front is implied. And then my exponents, I know I have this equation. And I solve for x, and we get to 126. So this is our 32-bit number in IEEE floating point format. So the sign bits, the exponents with the added bias, and then our mantissa or fraction bits. Right? So the other probably most common mistake is forgetting this bias. So then the next thing that we can do is, what is the value of the following IEEE binary floating point number? And this one I want you guys to work on your own. Because we now know the formats, we know how to convert, we've done an example, and now we just want to go the other way. So your poll for today code is 077.
What are the options?
Just to answer when you're done.
Oh, just think you're done.
Zero seven seven. Most people are done working on this one immediately. Just go over your answer with the people around you, walk through it step by step, and then when you are done, change your answer to, no one has answered E, so change your answer to E when you are done with the hearsay.
Right.
And then the flip
I know that
will be coming secondly.
About you.
Yeah, these are just extras.
Yeah, so this. What's up?
What's one?
What's quite good, but it's our because sections here comes to we don't have
I hear discussion dying down, but not so many people have switched their answer to A. Right. So going over this together, sine beta is 0, so my answer is positive. The exponent, if I convert it, 128. What do I need to do to this exponent?
minus the bias.
Minus the bias. The bias is 127. So my real exponent is, and then my fraction is 0.11. So that means that my significand, which is the whole thing, is 1.011, right? Because we have the implied 1, right? So 1.011. And we have this as our exponent. So we get this, but we're going to then shift it because of the 2 to the 1. We get 2.75. Okay. Because we have 1.011, we shift the decimal to the 1 over by 1. So this is 2, 1, 0, right? And then 1, 1 is 0.5 plus 0.25, 0.75. So 2.75. Right? So this is another question. So everyone has answered E right now. But what I want you to do for this one, I think it has. No, it doesn't have an answer. So just if you think A is larger, answer A. If you think B is larger, answer B. Okay, if you haven't answered yet, go ahead and just put in your best guess that you have, and then you can start the peer discussion. Submit your answer. You are convinced to change your answer.
What is so that it can be larger and still negative?
Yes.
Because it's positive, so it's gonna be negative. Bigger number.
So that
Yeah,
both
negative.
technically, some more negative one.
Bigness instead of positive is larger.
I thought it meant positive.
But that's not.
I thought it was
That's what I'm hoping. Let's see.
The two do. Yes. Yeah, you were putting.
Basically, there's a provide area, which like plus the smaller. So it's negative.
Yes.
So we convert A. We get the exponent is 63, so we subtract the bias. It's 2 to the negative 64. And we can just, because the exponent is going to tell us a lot about their relative magnitudes to each other, we can kind of ignore the fraction bits. Okay. We can just say that A is going to be negative and it's going to be shifted to the left by 64. So this is a really, really, really small number close to 0. Okay. And then B, it has a much larger exponent. It's 142. So we subtract 127. We get that its real exponent is 15. So this one is going to be shifted to the right by 15. So this is going to be a really, really large negative number. And we're asking which one is larger. They're both negative. This one is closer to 0. So A is larger. Right? B is a very large number, but it's negative, right? So it's very, very far down on the wrong side.
And
Alright, so just as a recap, this is our representation. We have the sign bits, the fraction bits or mantissa, and then the exponents. And this is how they are laid out. 1 bits of sign bits, 8 bits of exponents, 23 bits of fractions or mantissa. And the key thing to remember is the first bit to the left of the decimal point is always implied 1. And you have to also add in the bias to the exponent. Those are the 2 key things that are often just forgotten. Yep. That is floating point representation. And here's just a little bit about the range. So the smallest value of single precision is going to be shifting to the left by 126. And you have all zeros as your fraction bits. So this is the smallest value that you can represent. It's approximately equal to 1.2 times 10 to the negative 3. And then the largest value is going to be 254 minus 127. And if we figure that out in decimal, it's 3.4 times 10 to the W. And this is positive or negative. And by smallest, we just mean how close can we get to 0? And then same thing for self-precision. You can get a lot smaller, a lot larger. Alright, so for Wednesday, we will go over how to do addition and multiplication and loading my numbers. And you have a reading for this. And once you posted, homework has been posted, yes. And once you're done with that, you'll be able to finish it. So like I mentioned, homework will be due next Wednesday before.